Just before the October break, we were looking at this new type of gradient that we call the displacement gradient, and we showed that the deformation gradient F can be expressed as identity plus the gradient of U with respect to the undeformed Z coordinates. And I showed you how to construct it from the black deformed tangent vectors to the blue deformed tangent vectors. The red vectors that connect them give you this displacement gradient ellipsoid. Excuse me. We also looked at this definition of a linearized strain, which, as I showed you last time, does not include this nonlinear term. So if you write the definition of the Green Lagrange strain in terms of the displacement gradient, there is this nonlinear term that causes this definition of strain to be nonlinear. And I think I showed you that this definition of strain is the same definition of small linearized strain that you might have seen in your undergraduate mechanics of materials. And we also showed last time that it is really only the correct or the large deformation strain that comes out zero if you have a rigid body motion. In the small deformation definition of strain does not give you zero even under rigid body motion. Even under rigid body motion you get some non-zero strain, which is not good. So that's why linearized strain is not good. So I think that's about where we were last time. So does anybody have any pressing questions about what we did before the break?
No. No.
Okay. By the way, is any part of my screen blocked out? Are you able to see my entire screen?
Yes, we can.
Okay. All right, good. So let's continue on with a related topic, which is compatibility of strains. So now this, what this topic, it's actually not even in your books, but this is something just for your awareness that there is this issue that comes up sometimes. What this issue of compatibility deals with is the fact that not all possible strain tensor fields are compatible in general. Now the way we have defined strains by starting out with a map, right? So if you know the map, then you can express the map in terms of the undeformed position Z plus a displacement. And if you compute strains from this by doing half of gradient of U plus half of gradient of U transpose, then you know for a fact that this strain comes from a displacement or a physical displacement or an actual map. There is no issue here. So compatibility is automatically satisfied. But if somebody asks you the reverse question, that if I give you a strain field over a body and I ask you, can you tell me what is the underlying displacement field or the map? Then that question cannot always be answered unless certain conditions are satisfied. So for example, you might have like some square plate onto which on that square plate you have installed a few strain gauges and you're measuring strains at different points in the square plate. So let's say you measure the strain field, the strains at some points, and you interpolate to find the strain tensor at each and every point in the square plate, and that would be something like a strain field. And since these are measurements, there might be some errors in there. So the natural question is that given this strain field, can you tell me what the underlying displacement field is? And in order for that question to be answered, we must have compatibility of strains. We can find a displacement field if the strains are compatible. It is very easily possible that the measured strains are giving you a picture something like this, like the blue parallelograms in this picture. These blue parallelograms don't really fit together. There's overlaps and there are gaps. So this strain is not compatible. Okay. So the question is that should we, what conditions do we need to impose to make sure that the strains are compatible? So to do that, what we'll do is we'll derive these conditions, and we'll do that by considering the normal strains first, epsilon 1, 1. We know from the definition of small linearized strain that this is equal to partial U1, partial Z1. So maybe I'll remind you of that. You remember last time we said gradient of U, the components will be partial UI, partial ZJ, EI, dyad EJ. Okay. So, and actually this should be GJ. Just like the deformation gradient, there are two legs to this vector. So, so in the same way, if I now take a derivative of this left-hand side, epsilon 1, 1, double derivative with respect to Z2. So I'll just take a double derivative of this. What we get is partial U1, partial 3 of U1 and partial Z1, partial Z2 square. All I did was take this double derivative of epsilon 1, 1 with respect to Z2. I'll do the same thing for epsilon 2, 2, partial of U2 with partial Z1 squared, partial Z2. Okay? So, so we get these two terms here, and we are looking at, let's take a look at the shear strains now. These are the normal strains. The shear strains are partial U1, partial Z2, partial U2, partial Z1, and the whole thing is half, so I've moved the 2 to the other side. This is coming straight from the definition of linearized strain. So now if I take the double derivative of E12 with respect to Z1, Z2, that's what this is. I just take the double derivative of this entire thing with respect to Z1, Z2. Let's see what we get. We get partial cube U1, partial Z1, partial Z2 squared, plus partial cube of U2 and partial Z1, partial Z1 squared and partial Z2. Now note that if I take this and add them together, I should get these two terms, right? Which is basically what this first condition says. The sum of this plus this is equal to this. That's one of the compatibility conditions. And if you switch, instead of 1, 1, 2, 2, if you have 1, 1, 3, 3 or 2, 2, 3, 3, then you get two more equations. I hope this is just algebra. I'm sure you can do that, but it's these conditions, this condition and two other similar conditions in terms of 1, 1, 3, 3 and 2, 2, 3, 3 that would that give you compatibility of strains or partial compatibility of strains, and then you have three other equations also. So in order to derive those, we'll take a look at this definition of the shear strain again. epsilon 1, 2 is equal to partial u1 partial z2 partial u2 partial z1. Now I'll take the derivative of that with respect to z3. And if we do that, we get these terms. All we are doing is derivatives with respect to z3. Similarly, for the 2-3 strain, derivative with z1 gives me these two, and 1-3 shear strain with respect to 2 gives me these two terms. And what we'll do now is a little bit of algebra. I'll take this row and multiply that with -1. Take this row, add that to it with a +1, and take this row and add it with a +1. So if I do that, hopefully you can see that some of the terms will cancel off. So for example, partial u1, z2, z3. This guy and this guy will cancel off. So let's do that. That term and that term cancels off. Partial u2, z1, z3. Partial u2, z1, z3 is right here. These two terms cancel off. And what we have left is partial of u2, partial of u3 with z1, z2, and partial of u3 with z1, z2, the same thing. So that gets added together, half and half become 1, and that's what I have here, right? So if I subtract the first term, add the second and the third terms, I get this on the right hand side. Now, what I'll also do is I'll take the derivative on the left hand side again with respect to z3. So partial z3, partial of z3, and on the right hand side, what we see is partial, this becomes triple partial, but so partial of u3 with z3, that is epsilon 3,3. That's what I have here, and the derivative of that with respect to z1, z2, that's written down here. So we get yet another compatibility equation using the shear strains only. And as you can imagine, if I switch the order, placing this minus sign here and then here and adding the other two, I'll get two more equations. So in total, there are these 6 equations of compatibility, which when satisfied, then you can say that yes, the answer to this question is that if the 6 conditions of compatibility are satisfied for a given strain field, then there exists underlying displacement field or a map that is compatible with these strains. Otherwise the deformation might look something like that. So again, this is a concept that I think it's important to understand, but in our approach, we will most of the times go with finding a map first, from the map finding displacement, and from the displacement finding strains. In that case, it will always, compatibility will always be satisfied. And a shorthand notation of that, 6 relations of compatibility is given here, which again I'll not go into the details of that meaning. But if there are any questions on any of these steps, I can take them. Otherwise, we'll keep going.
There is no questions.
Okay. All right. So let's take a look at the topic of how do you find out local and global changes in areas and volumes. Now, you remember from quiz 2 that we've already done local changes in length of curves, right? So for example, if I gave you an undeformed curve right here, and through the deformation that curve got extended or contracted, we know how to find the undeformed length of the curve. We know how to find the deformed length of the curve. So for example, the deformed length of a curve you would find as integral of dx, which you can directly find if you know the parameterization, of the deformed curve. So that again is not too difficult, because if you know the parameterization of the undeformed curve and if you know the map, then you can directly write the parameterization of the deformed curve, and you can directly find this this deformed length. Or you can also find it by integrating lambda of z of s and times dz ds and ds. Okay, so this is something that we have done. What we'll try to do now is to extend the same ideas to find changes in areas and volumes. And also long back, well, for homework 1 and 2, I believe, we found how we set up parameterizations, and then we use those parameterizations to find areas of surfaces, complicated surfaces in 3D, right? So we do that by, if you remember, we did that by this way, that we can define a surface in terms of two parameters, let's say S1 and S2, and so we can come up with tangent vectors to curves that define the surface. That would be, for example, this tangent vector. I'm going to call that vector dz ds1, and the other tangent vector here, I'm going to call that dz ds2, right? And these are nothing but, the way I'm defining them is, this is n1, this is n2. And if you remember, we said that the local area would dA would be n1 cross n2, ds1, ds2. So this is nothing but dz ds1 cross dz ds2, ds1, ds2. And if you integrate that, you get the total area. If you integrate that, you get the total area of a surface, of course, under the right limits. So this is something that we had done. Now, for the deformed area is obtained by just applying the map to this tangent vectors. So maybe let me ask you this first. I have the undeformed tangent vectors n1 and n2 here. And if I take n1 cross with n2, I get this vector m. So maybe I'll write that here. M is equal to n1 cross n2. And to make it a unit vector, I'm going to divide it by its magnitude. So n1 cross n2 divided by its own magnitude gives me the unit vector. So, and similarly, if I define, well, maybe before I go to the deformed one, I'm asking you whether if I take the F deformation gradient, apply it on F on the N1 tangent vector, I get this tangent vector, which is what I'm calling Fn1. So this deformed tangent vector is dx ds1, and this Fn2 tangent vector is dx ds2. So we know that F will act on these undeformed tangent vectors n1 and n2 to take them to Fn1 and Fn2. The question is that will this deformation gradient also take the tangent vector that a vector that is perpendicular to these two tangent vectors, which defines the cross product M. M is defined as a cross product. If I take F acting on M, will it give me the normal vector to the deformed tangent vector, to the deformed area? And I suppose this is a difficult question to answer for out of intuition. You might be intuition might tell you that I have a normal vector which is perpendicular to both n1 and n2 in the undeformed configuration. And if I'm taking a look at the normal vector to the deformed tangent vectors fn1 and fn2, that the f would also take that this normal vector to this normal vector, but that is not true. So that this new normal vector to the deformed surface is obtained by taking by doing the exact same thing to f acting on n1, that's the deformed tangent vector, cross product with f acting on n2, the deformed tangent vector, divided by its magnitude. So again, fn1 cross with fn2. And using these deformed tangent vectors and the normal vectors, we'll define the deformed area. dA, the deformed area, is going to be simply exactly the same way that we deform when we define the undeformed area. We'll define the deformed area as f acting on n1 cross product with f acting on n2 and ds1 ds2. All we did was replaced the undeformed tangent vectors with the deformed tangent vectors. Okay. Now, if I multiply that with the normal to the deformed surface, then actually all I'm doing is taking the magnitude, multiplying it with a unit vector. So this norm and this norm in the denominator will cancel off, and what we get is something like f acting on n1 cross with f acting on n2 ds1 ds2. And the next few steps are just algebra, but it will help us to get to a point where we can use this relationship for deformed areas. So what we do next is pre-multiply this entire equation. Pre-multiply this entire equation with F transpose. And you can see F transpose N would be equal to F transpose, all the same thing here. And then we'll use an identity or a theorem from our textbook, that theorem number 147b that's given in the textbooks. We can show that F transpose acting on Fn1 cross with Fn2 is equal to determinant of F, which is a scalar, multiplying the vector N1 cross N2. Okay. So just by some rearrangement, we get NDA on the left-hand side. If I pre-multiply by F inverse transpose now, F inverse transpose times determinant of F times N1 cross N2, ds1, ds2. This is a big sort of complicated relationship. But what's good about this is that it relates the deformed area and its unit vector to the undeformed area and its unit vector with this factor, F inverse transpose times determinant of F. So this is a very popular formula which is called the Nansen's formula. Let's write this one out. Determinant of F, F inverse transpose, M and DA. And actually M should also be black. That's the undeformed vector. So Nansen's formula or parallel transformation, this is basically something that that allows us to calculate, to express the deformed area in terms of the undeformed area. And a couple of other quick relationships related to this is dA, the ratio of the deformed versus the undeformed is simply given by this this relationship. If I just take the norm on, or these are both vectors on left and the right hand side, if I take the magnitude or the norm of those, the ratio would be simply the factor that we just introduced, determinant of f, which is a scalar, and F inverse transpose, that is a tensor, by the way. F inverse is a tensor, transpose again is a tensor. So that acting on this undeformed normal, and then you take the norm of that. That factor is the relative change in area of at a point, locally at a point. So at this, for example, at this particular point, I had N1, N2 that went to Fn1 and Fn2. So this small area, capital dA, went to this small area, small dA. The ratio of those areas is given by this expression, determinant of F times the norm of F inverse transpose acting on M. This is a tensor, acts on a vector to give me a vector, and I take the norm of that vector to give me that ratio. Okay? So with all of that, we can find the deformed area as the double integral of dx ds1 cross dx ds2, norm of that, ds1, ds2. Now, just like the undeformed and the deformed lengths, if you have the parameterization of the deformed surface, you can directly use that relationship to calculate the deformed area, okay? And alternatively, you can substitute all of this that we have just derived to show that the deformed area can be expressed as the integral over the undeformed area now, which would be of determinant of, maybe I'll write that in blue again, determinant of F, there's a tilde here, and norm of F inverse transpose M, and norm of F inverse transpose M, and dA, which would be equal to dz ds1 cross dz ds2 dz ds2 and norm of that times ds1 ds2. So just like changes in length, if you want to find the deformed length, you could directly do that if you have the parameterization of the deformed curve, or you can express the same thing with a stretch times the DL corresponding to the undeformed curve. That's exact same relationship I've written down here below, or the corresponding relationship for areas. The deformed area can be written in terms of the parameterization of the deformed surface, which can be expressed in terms of the parameterization of the undeformed surface times the stretching factor for the areas. So either of these two you can use to calculate the changes in area. Okay, and I know there's a fair bit of algebra here to digest, but it's just that, it's algebra. I hope you can go through and derive it for yourself and convince yourself that if you can find the undeformed area of a surface, something that we did long back, you can always find the deformed area of that surface, no matter how complicated that deformation is. Okay. So if you know the map and if you know the parameterization of the undeformed surface, you can find the area of the deformed surface. All right, so very quickly, I'll also talk about change in volume, which is actually much simpler than area. But if you remember, we said that local volume, if I gave you a parameterization of a body, let's say this body, we have this black body, and I'm considering this partial volume of that body. So if I want to find the volume of that body, I need a parameterization in terms of 3 parameters, S1, S2, and S3. And the tangent vectors corresponding to those 3 parameterizations would be N1, N2, and N3. And if you don't remember that, maybe long back, you remember volume of a body was given by dx ds1 cross dx ds2 cross dx dx3 and ds1 ds2 ds3. That's the volume of a body if you know the parameterization. So the same thing we are doing here. That's the undeformed local volume. The deformed volume would just be the corresponding mapped tangent vectors Fn1 cross Fn2 and then the dot product with Fn3. And again, with a theorem in the book, you can show that that this quantity in the brackets in here is equal to determinant times the same thing for the undeformed tangent vectors. So the deformed volume is much simpler. We get directly that determinant of F times the undeformed volume. That's the relationship for deformed to undeformed volumes. And finally, if you can find the volume of an undeformed body, given the map, you can always find the volume of a deformed body, which would be equal to, again, I'll write that long expression where you can express this as F N1 cross F N2 dot with F N3 ds1 ds2 ds3, which would, so this would be the deformed volume if you know the parameterization of the deformed, if you know its parameterization. If you don't know its parameterization, and if you know only, or if you want to calculate that volume only using the parameterization of the undeformed volume, you can simply write that as triple integral of determinant of F and the undeformed volume, which is this one right here. So let's see if I can capture that. Copy and paste. So both of these are equivalent ways of finding a deformed volume if you know the undeformed volume. And since I don't have time to go through this example, I'll let you read this example actually from the book. And this was an exercise. What I'll do is I'll post this example along with my lecture notes onto Blackboard, and then we'll also do that similar examples in the review session on Friday. I think that should allow you to pretty much complete homework 5. But if there are still lingering questions, then we can try to address them on Friday. Okay, looks like, sorry for all the trouble with WebEx. I think we still were able to cover most of the things that we wanted to, and hopefully if you have questions, you can post them on the Blackboard. Otherwise, I'll see you on Friday. And thanks, Hugo.
Okay.
So I'll sign off here, okay?